Quantum mechanics, QM, also known as quantum physics, quantum theory, the wave mechanical model, or matrix mechanics, including quantum field theory, is a fundamental theory in physics which describes nature at the smallest, including atomic and subatomic scales. It results in what may appear to be some very strange conclusions about the physical world. At the scale of atoms and electrons, many of the equations of classical mechanics, which describe how things move at everyday sizes and speeds, cease to be useful. In classical mechanics, objects exist in a specific place at a specific time. However, in quantum mechanics, objects instead exist in a haze of probability. They have a certain chance of being at point A, another chance of being at point B, and so on. Quantum mechanics, QM, developed over many decades, beginning as a set of controversial mathematical explanations of experiments that the math of classical mechanics could not explain. It began at the turn of the 20th century, around the same time that Albert Einstein published his theory of relativity, a separate mathematical revolution in physics that describes the motion of things at high speeds. Unlike relativity, however, the origins of QM cannot be attributed to any one scientist. Rather, multiple scientists contributed to a foundation of three revolutionary principles that gradually gained acceptance and experimental verification between 1900 and 1930. They are: quantized properties. Certain properties, such as position, speed, and color, can sometimes only occur in specific, set amounts, much like a dial that clicks from number to number. This challenged a fundamental assumption of classical mechanics, which said that such properties should exist on a smooth, continuous spectrum. To describe the idea that some properties clicked like a dial with specific settings, scientists coined the word quantized. Particles of light. Light can sometimes behave as a particle. This was initially met with harsh criticism, as it ran contrary to 200 years of experiments showing that light behaved as a wave, much like ripples on the surface of a calm lake. Light behaves similarly in that it bounces off walls and bends around corners, and that the crests and troughs of the wave can add up or cancel out. Added wave crests result in brighter light, while waves that cancel out produce darkness. A light source can be thought of as a ball on a stick being rhythmically dipped in the center of a lake. The color emitted corresponds to the distance between the crests, which is determined by the speed of the ball's rhythm. Waves of matter. Matter can also behave as a wave. This ran counter to the roughly 30 years of experiments showing that matter, such as electrons, exists as particles. Quantization helped to explain other mysteries of physics. In 1907, Einstein used Planck's hypothesis of quantization to explain why the temperature of a solid changed by different amounts if you put the same amount of heat into the material but changed the starting temperature. Since the early 1800s, the science of spectroscopy had shown that different elements emit and absorb specific colors of light called spectral lines. Though spectroscopy was a reliable method for determining the elements contained in objects such as distant stars, scientists were puzzled about why each element gave off those specific lines in the first place. In 1888, Johannes Rydberg derived an equation that described the spectral lines emitted by hydrogen, though nobody could explain why the equation worked. This changed in 1913 when Niels Bohr applied Planck's hypothesis of quantization to Ernest Rutherford's 1911 planetary model of the atom, which postulated that electrons orbited the nucleus the same way that planets orbit the Sun. According to Physics 2000, a site from the University of Colorado, Bohr proposed that electrons were restricted to special orbits around an atom's nucleus. They could jump between special orbits, and the energy produced by the jump caused specific colors of light, observed as spectral lines. Though quantized properties were invented as but a mere mathematical trick, they explained so much that they became the founding principle of QM. Also in 1927, Heisenberg made another major contribution to quantum physics. He reasoned that since matter acts as waves, some properties, such as an electron's position and speed, are complementary, meaning there's a limit, related to Planck's constant, to how well the precision of each property can be known. Under what would come to be called Heisenberg's uncertainty principle, it was reasoned that the more precisely an electron's position is known, the less precisely its speed can be known, and vice versa. This uncertainty principle applies to everyday size objects as well, but is not noticeable because the lack of precision is extraordinarily tiny. According to Dave Slavin of Morningside College, Sioux City, IA, if a baseball's speed is known to within a precision of 0.1 miles per hour, the maximum precision to which it is possible to know the ball's position is 0.000000000000000000000000008 millimeters. For more information, check out Fundamentals of Quantum Mechanics by J. E. House.